Well, good morning, everybody. So today I'm going to do an introductory lesson to simplifying radicals. I do a lesson real similar to this when I cover simplifying square roots that have variables in them. But this one I'm going to do just has pure numbers in it. My notes are going to come from page 77 and 78. This goes along with the homework assignment on page 79, and the homework assignment has the title Simplifying Radicals. Before I move to page 77, though, there is something that I will be doing in this lesson and on most of my problems called prime factorization that I want to make sure you know how to do. So prime factorization. Now, what we're going to do, you can do this with absolutely any number that's not prime. Let me go ahead and just choose one. Let's go with the number 20. So if you take the number 20 and think of any two numbers that will divide 20 evenly. I'm going to do this twice just to show you that we end up with the same numbers. So the way I like to show this is let's go with a simple one first. Let's do 10 times 2. Well, 10 times 2 equals 20. 2 is a prime number, a number that can only be divided by itself. 10 can be further divided. I know that 10 breaks down into 2 times 5. 2 and 5 are both prime factors, so 20 can be broken down into the prime factors 2 times 2 times 5. Now let's see what happens if we break 20 down, starting off with two different numbers. I also know that 5 times 4 equals 20. 5, once again, is prime. 4 is not because it can be broken down into 2 times 2. And just like we did the last time, we ended up with 2 times 2 times 5. And that's what I wanted to demonstrate for you. To simplify radicals, we are going to use prime factorization on the number underneath the radical sign. And we will end up with its prime factors, and I will describe for you here in a moment how we use those prime factors to simplify the radical itself. So prime factorization, you just divide it by any two numbers that you can think of that multiply to equal that value. Break down each number that's not prime until all the numbers that remain are prime numbers. Okay, well, let's jump to page 77. Let's talk a little bit about most of you may call this a square root sign, but it's more appropriately called a radical because this symbol, that check mark symbol, can be more than just square roots. We've got cube roots, and we can go to the fourth and the fifth and the sixth root, whatever you needed to do. Now, there are three different components of it. And the one that I think is the most foreign to algebra students is going to be this one here. Just inside the little pocket of the check mark, we have a number that we call the index. Now this index is going to, later on when I describe it, is going to tell us what size of groups we're looking for within our prime factors. Now, the check mark, I better use the correct word, is called the radical. This is a radical sign. And the number inside the radical symbol is called our radicand. Okay? So, now there is an important thing that I kind of alluded to a second ago. If you are looking at just a normal square root symbol, all right, if there is no number written inside this check mark, if there is no index, then it's assumed that the number that is there is a 2, all right? So just keep that one in mind, that there is always a number inside that little check mark. If there's nothing written, it is assumed that it says 2, otherwise there will be a number written there. Now, the note-taking guide takes an interesting method to solving these, and I'm going to go ahead and use it on 1 through 9 to demonstrate some basics of breaking these down. But they had me list the first 12 perfect squares. Now, perfect squares are going to be numbers that break down into perfect doubles. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 5 times 5 is 25. Let's just keep this going because we don't have all of them. 6 times 6 is 36. 7 and 7 is 49. 8 and 8 is 64. 9 and 9 is 81. 10 and 10 is 100. 11 and 11 is 121. 12 and 12 is 144. And then here on the very end, we've got one that you probably don't have memorized. 13 times 13 is 169. So it is helpful to attempt to, before prime factorization, if you can recognize that one of these numbers, if one of these radicands can be divided by a perfect square, then you won't have to further break that down. You'll see that we can simply cross that out and take it outside the radical. For instance, square root of 81, that happens to be one of our perfect squares. So this breaks down into 9 times 9. Our index, since there is no number written there, is a 2, which means we're looking for groups of 2. For each group of 2, that couple becomes one number. So we take 2 9s in the radicand and we bring them outside to make a simply a 9 on the outside. So for every pair in the radicand, we bring one of those out outside the radical. Now, if everything under the radical sign finds a perfect match and goes outside the radical, the answer to the square root of 81 is 9. I'm going to do this on each of these. Now, 484, that's a number that we're a little bit less familiar with. 484 is a perfect square, but it's not in our list. 484 breaks down into the square root of 22 times 22. We have a couple here, so these two 22s leave the radical sign and become a single 22 on the outside. Everything under the radical was crossed off, so the square root of 484 is 22. We've got another perfect square here, 64, and that breaks down into 8 times 8. The index is 2, so we're looking for groups of 2. The groups of 2 get crossed out, come to the outside, and become a single 8. So the square root of 64 is 8. Now we get to some that have numbers on the outside already, and then we also have on 7, 8, and 9 ones that are fractions. So let's see how we deal with that. So the radicand is a perfect square. So we have 18 radical 2 times 2. 2 and 2 make 4, that's our radicand. The 2 goes to the outside and is going to multiply by the value that is outside the radical. The radical sign disappears because everything got crossed off. 2 times 18 makes 36. So 18 times the radical 4 is equal to 36. Let's do this again here with a larger number, 256. There's another one that's a perfect square that you might not recognize. 256 breaks down into 16 times 16. So the two 16s go to the outside, and they're going to be multiplied. That single 16 we bring out is going to be multiplied by the 3 on the outside of the radical. 16 times 3 equals 48. And so there we are. Let's go ahead and let's do one here that's got a negative number on the outside. It's going to function the same way. 121's in our list of perfect squares. So we have negative 5 radical 11 times 11. That pair of 11s becomes a single 11 on the outside of our radical sign and multiplies by negative 5. Everything under the radical was crossed off, so all we have to do is 11 times negative 5 for a solution of negative 55. Now, when you have a fraction under the radical sign, there is a step here that may be new to you. When you have a numerator and denominator under a radical, you can separate this into two radical symbols. Radical 1 over radical 16. Both of those happen to be perfect squares. This one is 1 times 1, so radical 1 is equal to 1. This is 4 times 4, so radical 16 is equal to 4. And our final solution in this case, radical 1/16 is equal to 1/4. We're going to do it again here with 8. Radical 9 over radical 100. 9 breaks down into 3 times 3, so the square root of 9 is equal to 3. 100 breaks into 10 times 10, so radical 100 is equal to 10, and our final fraction here is equal to 3/10. Let's do it one more time here with number 9, and then we'll get into some more interesting problems. So we have radical 25 over radical 49. 25 breaks down into 5 times 5, so square root of 25 is 5. 49 is 7 times 7, and so that becomes a single 7 on the outside. So the square root of 25/49 is equal to 5/7. Now, what we're going to do is start looking at ones that are not perfect squares, where not everything is going to match up, and we'll still have a radical in our answer. Now, they gave you a 3-step process here. That's not bad. They tell us find the largest perfect square that the radicand is divisible by and break down the radical using this number. I prefer simply to call the first step prime factorization. Take that number and break it all the way down to its prime factors. Now, you can look for perfect matches. Okay, I call it the dating game. So we're looking for perfect matching couples. And to help you remember this, I make it real corny. So once you find a perfect couple, all right, they get married, they become one person, and they leave the radical sign altogether, and they leave behind all those people that didn't match up. Once you've done this, any numbers that remain under the radical sign, we are going to multiply back together. Any numbers on the outside will multiply the way we did up here. So let's just go through this process. First, I'm going to do the prime factorization of 24. 24 breaks down into 6 times 4. Neither of those are prime. 6 breaks down into 2 times 3. 4 breaks down into 2 times 2. And now we have 4 prime numbers multiplied together equal 24. So let's see what we can do with that. We have a radical 2 times 2 times 2 times 3. 2 times 2 times 2 times 3. My index is 2, since nothing is written there, which tells me I'm looking for couples. I have a perfect couple here. The 2's get married, they love each other, and they become one person on the outside of the radical. The 2 and the 3 that remain on the inside, well, they didn't find a perfect match. So we have found all the couples that are there. So there was nothing for me to multiply this 2 by on the outside. So I have 2 radical, and on the inside I still have 2 times 3. So my solution is 2 radical 6. Okay, so let's do problem number 11. Once again, the radicand is, or not the radicand, the index is 2. So we're looking for couples. We're going to break 48 down. 48 breaks down into 2 times 24. We've got our first prime number. 24 breaks down into 6 times 4. We just did this one. And that breaks down into 2 times 3 and 2 times 2. So now we have radical 1, 2, 3, 4 2's. 1, 2, 3, 4 2's and a 3. And this time, again, we're looking for couples. The index is 2, so we have a 2, a couple of 2's. We have another couple of 2's. So each of those couples becomes a single 2 on the outside, and now we remultiply whatever remains. The 2's on the outside multiply together, and the only thing that didn't find a match on the inside was this 3. It remains under the radical sign. 4 times radical 3 is our final solution on that one. Let's do this again with problems 13 and 14. So 63, I'm going to go ahead and start breaking it down into its prime factors. That's 9 times 7. 7 is prime. 9 breaks down into 3 times 3. So we have 3 times 3 times 7. The index is 2, since nothing's written there, which means we're looking for couples. I have a perfect couple here. They go outside the radical sign and become a single 3. The 7 and the 3 have nothing to be multiplied by at this point, so my answer is 3 radical 7. And let's do 90 here finally. So 90 breaks down into 9 times 10. 9 breaks down into 3 times 3. Those are both prime. 2 times 5. Those are both prime. The index is 2, so we're looking for couples. And let's simplify this all the way. We have 2 times 3 times 3 times 5. We've got a pair of 3's right here that go to the outside and become a single 3. Whatever remains on the outside and the inside get multiplied. The 3 has nothing to multiply by, so I have 3 radical. Now 2 and 5 remained under the radical. 2 times 5 is 10. So 3 radical 10. Let's turn our page, and because all we've been doing is square roots so far, I think I may have told myself I was going to do at least one more like that. Let's see here. No? Let's go ahead and let's talk about perfect cubes. So when we did perfect squares, we were looking for doubles that multiplied together to equal a value. Now we're looking for triples. So 1 breaks down into 1, 1, 1. 8 breaks down into 2, 2, 2. We have 3, 3, 3 multiplied together to equal 27. We're going to keep this process going. 4 times 4 times 4 is 64. 5, 5, and 5 is 125. 216 is going to break down into 6 times 6 times 6. We have 7 times 7 times 7 make 343. 512 is 8 times 8 times 8. 729 is 9 times 9 times 9. And finally we have 10 times 10 times 10. So this time our index is going to be 3, which is a perfect cube root. This time, instead of looking for couples, we are looking for groups of 3. So let's take a look at number 8. I break this 8 down into its prime factors. I'm looking for groups of 3. The index is 3. 8 breaks down into 2 times 2 times 2. And each group, each perfect group of 3 becomes a single 2 on the outside. If everything under the radical is crossed out, the cube root of 8 must be equal to 2. I'm going to do each of these ones here real quick. Now 729 is in our list of perfect cubes. So we have 729 breaks into 9 times 9 times 9. We have a perfect group of 3. They go to the outside, perfect group of 3 9s. And so they become a single 9 on the outside. The cube root of 729 is 9. So let's see here. This one, 1331, I wouldn't have seen this right off the bat. That one breaks down into 11 times 11 times 11. That's the 11th perfect cube that we know. A group of 3, like my index tells me I'm looking for, go to the outside and become a single 11. The cube root of 1331 is equal to 11. So I think you guys are starting to get the idea. Let's take a look at one here that has a negative sign. Now you can't find the square root of negative, the square root of negative numbers, but you can possibly find a cube root. For instance, this one here, I'm still looking for groups of 3, breaks down into -1 times -1 times -1. That's a group of 3, and so they go to the outside, become a single -1. The cube root of -1 is -1. I'll do 26 as well. I am trying to keep the video a little shorter. Let's see here. -343 breaks down into -7 times -7 times -7. A perfect group of 3 go to the outside, become a single -7. So the cube root of -343 is -7. Let's go ahead and look at ones that have non-perfect cubes. I've got a couple of them marked here for us to do. So we're going to start this out the same way. We're going to do our prime factorization on problem 28 here. We're going to do our prime factorization of 40. 40 is 4 times 10. 4 is 2 times 2. There are some prime factors, and 2 times 5. I'm looking for a index of 3, so the cube root, I have 2 times 2 times 2 times 5. I'm looking for groups of 3 numbers that are identical to each other. I have 3 2s. They go to the outside, become a single 2. And just the same way we did earlier, we remultiply anything that's now on the outside and anything that remains on the inside. This time the 2 and the 5 are all that we have that's left over. So the cube root of 40 is equal to 2 cube root of 5. That's as simple as we can make it. Let's try a larger number, 500. So I went with 50 times 10. I could have done 5 times 100 as well. Would have ended up with the same prime factors. I have 2 times 25. 25 is 5 times 5. And 10 is 2 times 5. So I'm going to put these in order, make it a little bit more obvious to myself what I've got. I have a 2 and a 2, and I have a 5, and a 5. Since my index is 3, I'm looking for groups of 3 numbers. 3 groups, 3 5s become a single 5 on the outside. I remultiply what remains on the inside, and I have 5 cube root of 4 as my final solution. Let's go ahead and let's do one that has a negative number here. So problem 31 has a negative number. I'm going to break that down. Now, negative 16 can be rewritten as negative 2 times negative 2 times negative 2. I just kind of jumped ahead a little bit on that one. So we have cube root of negative 2, negative 2, negative 2. A perfect group of 3, as our index tells us we're looking for, come to the outside and become a single negative 2. So the cube root of negative 16 is going to be negative 2. That one worked out real cleanly. Let's do one that doesn't work out as cleanly. Let's try 432. I didn't know what this one broke down into at first. I got 2 times 2, 16. 216 is one of our perfect cubes, remember, and breaks down into 6 times 6 times 6. So now I can write this as the cube root of 2 times 6 times 6 times 6. With an index of 3, I'm looking for groups of 3 identical numbers. Those 6's come to the outside to be a single 6. And I write my final answer as 6 radical cube root of 2. Let's do another one here. Let's do one more. Okay, let's do problem 36. So problem 36, I've got a negative 875. So let's break this down into its prime factors. I went ahead and actually divided by 5. So I did negative 5 times 175. 175 breaks down into negative 5 times 35, and 35 breaks down into a negative 5 times 7. If I remultiply negative 5 times negative 5 times negative 5 times 7, I would get negative 875. I see that I have a group of 3 negative 5's here, so they go to the outside for negative 5 cube root of 7 as my final answer. So I hope that this helps gives you a head start on this lesson. I look forward to going over this in Google Meets with you guys. Talk to you soon.